Okay, it's saying it's now streaming live on YouTube.
Okay, I think we can start.
Okay. So today I will talk about universality theorems for oriented matroids and polytopes. And first, let me define some realization spaces. So first, realization spaces. We'll be concerned with two types of realization spaces. First one is realization spaces of oriented matroids. So suppose we have a point configuration, which is just endpoints on the plane. And well, let's denote it like this. Let our set 1, etc. n be the set I. And yeah, let our point be has coordinates x, y, and xi and yi. So from these, we get a map from the cube of the index set to -1, 0, 1. We just sends 3 indices into the sign of the determinant of the following matrix. Okay. Well, it's equal to 1 if pi, pj, pk is a triangle in and ejk go into counterclockwise order. Yeah, so okay, suppose we have something like this. It's 1, 2, 3, and 4. Then chi of 1 to 3 is, well, -1. Chi of, say, 4, 3, 2 is 1. And chi of 1, 4, 3 is 0 because they are collinear. Okay, yeah. For us, this will be an oriented matroid. Well, there is an abstract definition of a oriented matroid, but basically, well, all our matroids will be realizable, so they will be like this. So we don't need an abstract definition. Okay, suppose now we have some map. And we choose 3 indices, ejk, such that chi of ejk is equal to 1. Well, this choice of 3 indices we make because we want to, well, factor out a affine transformation. Let me, yeah, okay. So then we define a realization space of chi with this basis as a set of all configurations such that the rest matroid of this configuration is the given matroid, and the if vertex is the origin, the jth vertex has coordinates 1, 0, and the kth vertex has coordinates 0, 1. So this is a realization space of a given matroid. Yeah, and well, we chose these ej and k to factor out affine transformation. Like, we know that in any realization of this matroid, vertices with labels ejk should be in counterclockwise order, so we can map them into the standard 3 vertices. Okay, that's all for the definition of the realization space this thing is realization space of an oriented matroid. Are there any questions about this definition? Okay. Then let me define the second type of realization spaces will be considered. We'll consider. So let Q be a convex polytope in RD with vertices, say Q. Let's number them by index at J. So from this polytope, we get a lattice of its faces. So this is the faces of Q with the inclusion relation, and well, it's a lattice, face lattice of Q. And well, okay, for instance, I don't know, we can consider an example.
Do it includes empty set in this lattice?
Yes, it does. So for something like this, it's what? Well, we have the top face. We have 4 faces. And we have vertices. And we have, I can't really draw, well, we have empty set somewhere and it goes into these guys. Okay. Well, yeah, I think it's clear what is a face lattice. And yeah, so, and given some polytope, well, again, we need to fix some additional data. This time we fix a flag. So it's first you take a vertex, then take an edge, and so on. You take the whole. Yeah, and then you take the whole set, and well, you want to k-dimensional face to be exactly k-dimensional. So the dimension of the affine hull of the k-dimensional, well, of k points in k-dimensional phase. Yeah, and also, well, each time you add exactly one new vertex, which we'll call, well, it's GK. So for example, for our quadrilateral, we can take Q1 and then say this edge, Q1, Q2, and then Q1, Q2, Q3. And what is a realization space of a polytope with fixed? Well, we get a collection of d+1 points. Do I have enough space here? Sorry for this. Okay, so it's all the polytopes such that they have the same face lattice as Q, and also the same vertices and so on. Well, okay, we fix d+1 vertices D, D, U, A, D. Okay, is it readable or should I rewrite it probably? I can't hear you.
Maybe you can use a new sheet of paper.
Yeah, probably. Okay. Okay, sorry.
You can
Okay,
keep the previous one so that we can see both of them at the same time.
Can I really do this?
Yeah, something like that. I mean, the lower part. I think we only need the lower part of this.
Okay, let me do it like this. Yeah. Okay. Yeah, can you see it now? Yeah. So okay. Yeah, the realization space of a polytope with chosen D+1 vertices forming an affine well that are affine independent. It's a set of all polytopes such that these polytopes up have the same face lattice and also the vertices well the fixed vertices they are fixed the same as in Q. Yeah.
What do you mean by fixed vertices?
I mean that, well, we chose these D+1 vertices such that they are vertices of a initial polytope and they span and they are finally independent. Okay. And we say that, yeah, the vertices of, of polytopes in our realization space, well, these vertices we chose, they should be the same. Okay.
Is it what you denoted by J sub K?
Yeah, J sub K is, well, okay, we have these sets of indices.
Yes.
Each time we add one index in such a way that dimension increases by 1. And these are all faces. All Fi are faces. So first we choose a vertex, then we choose an edge that contains this vertex. Then we choose a two-face containing this edge. Well, this is this one, but there are 4 vertices there. Yeah, but we choose only one. It's Q3, and so on.
So you demand that this, so to say, generating simplex in the first polytope is the same as in the second polytope.
Yeah, because if it's not the same, then since we can just use an affine transformation to make it the same, and affine transformations don't really we are not interested in them. We want to factor them out, and it is the way we do it. Mm-hmm. Yeah, okay. So these are realization spaces. Now let me say something about semi-algebraic sets. Suppose we have 3 collections of polynomials. And these are Fs. That would be collection F. These are Gs. And these are H. These are polynomials with integer coefficients. Then a basic semi-algebraic set V of these 3 families is just a set of all points in Rn such that for the polynomials from the first family, the values of these polynomials are equal to 0. For the polynomials from the second family, they are less than 0. And for polynomials in the third family, they are no more than 0. Okay, this is a basic semi-algebraic set, and it is called primary if we don't have any non-strict inequalities. So, for example, the set of 2 points or an interval in R, these are primary basic semi-algebraic sets. And a segment on a line.
Вот это уже не видно.
Oh, okay. And the segment on a line is a basic semi-algebraic set, but it's not primary because you cannot define it without using non-strict inequalities. Okay, and now we have the first proposition. So that these spaces, the realization spaces we've just defined, so realization spaces of oriented matroids, and well, if we took first a rational, the polytope, meaning that all its vertices have rational coordinates, then its realization space is a primary basic semi-algebraic set. Well, this one also. Okay, let's prove it. Well, for the first one, there is nothing to prove actually, because, well, what was our definition of a realization space? We wanted to the sign of some determinant to be fixed. Well, so we just say that the determinant is either equal to 0 or greater than 0 or less than 0. So our realization space is just, well, yeah, it's given by equalities and inequalities. Okay. So, and for, yeah, it's obvious. Yeah, for the realization space of a polytope, it's, well, it's also not that hard. So how to fix these? Well, we want to somehow write some inequalities and equalities such that they fix our phase lattice. Well, how do we do this? Well, let's for any facet and for any d points, well, the indices of this facet, we want to say that, well, okay, we take any facet. Can you see my hand? And we want to say that our polytope lies on the one side of this facet. And that's basically all. So if we have 2 indices not in our face, then the corresponding vertices should lie on the same side of the facet. So it means that, well, let me write it, minus determinant of, right, 1, then coordinates of qj1, so on, coordinates of qjd, coordinates of qi. You compute this determinant, then you compute this determinant, and it should be less than 0. Okay, we just have written an inequality of these, well, of the form we wanted. Yeah, it's a polynomial with integer coefficients. And yeah, this inequality exactly means that if and k vertices lie on the same side of facet F. Well, and also we should say that let's see. Do you want to ask something? Okay. Yeah, and also we need to say that, well, some vertices lie on the same facet. So if we take an index from the same facet, then the corresponding determinant Qj1 and so on, Qjd1 Qi, the determinant should be equal to 0. So yeah, and we have exactly said that, well, our polytope should have, well, we determined its facet, and it completely determines the face lattice of the polytope. So we've just proved that the realization space of a polytope is also a primary basic semi-algebraic set.
Sorry, Daniel, we have two new participants. Maybe you can very briefly repeat what you said before.
Okay. So first, the realization spaces. The realization spaces for arranged matroids. For us, arranged matroid is just an alternating map from the cube of index set to -1, 0, 1. And yeah, well, from a point configuration on a plane, you can get such a map just by saying for each triple of indices, either the corresponding triple of vertices of points is well, lies in counterclockwise order or in clockwise order. So you can see this example. I think example is enough to understand the definition of this chi. Yeah, and then from a given chi, you get a realization space, which is just.
Sorry, maybe it can be said in a more less technical way that we just have a configuration of points in R2, and we want to remember which of them lie on the same line, and also we want to remember the signs of the areas for each triple of points.
Yeah, exactly.
Okay.
Yeah, and then, well, yeah, if you have this information, then the realization space of this information is just all the point configurations that have these type of collinearities and orientations. And we also fix some points just to factor out a function transformation. Okay, this was the realization spaces of oriented matroids. And also, if we have a convex polytope, then from this we get a lattice, just a face lattice of this polytope, and a realization space of a polytope is the set of all polytopes having the same face lattice. And we also fix some vertices because we want to factor out of function transformations. Now we've defined semi-algebraic sets, which are just sets in Rn defined by polynomial equations and inequalities. And we've proved that the realization spaces of matroids and realization spaces of rational polytopes are indeed primary semi-algebraic sets. Okay. So yeah, where do we go next? Okay. Yeah, now we want to discuss stable accuracies. Suppose we have two primary basic semi-algebraic sets, and well, consider and suppose we the canonical projection, we just forget about the last d coordinates, sends W to V. Well, we want to define an equivalence relation on the primary basic semi-algebraic sets. But first, we define stable projections. These are projections that depend, say, polynomially on the target. Let me clarify what it means. Well, we have some collections of polynomials with integer coefficients for some index at j. And also we have another collection of polynomials for some index at k. And yeah, these polynomials define, well, for any element in Rn, they define a linear functional on Rd in the following fashion. So let V prime be the element of Rd, then this linear functional, well, it's not linear, it's affine actually. Yeah, it's, well, first we need to compute these guys. This is a linear functional. We apply it to V prime, and then we add a constant. Well, it's an element of R. And the same for psi. And V is called a stable projection of W if W can be recovered from this data, namely that W is precisely the set of points such that for phi's inequalities, well, we have inequalities, and for psi's we have equalities. So something like this. Okay, what does it mean actually? Let me draw an example. Suppose we have some set, say this one. This is our set V, an interval.
Sorry, what is V prime? Does the definition say that there exists a V prime?
No, the definition say that, well, if you can see, well, that all your W is the collection of such V with primes. Not that it exists, but the W is all such V primes.
Okay, sorry.
Yeah, so let me draw an example. I don't know, I have something like this. Well, this is R, this is R2. And I don't know, you draw something. Yeah, and then you, where is W in this picture? You include this thing, you don't include this thing, and here is your W. Say, well, there are no equations in the definition of W here, only inequalities. So in each fiber over any point V, what you get, you just say that in each fiber, first, your V prime should lie in some linear, well, no, some affine subspace. And second, it should satisfy some linear, again, well, it should be bounded by some hyperplanes. So basically, each fiber over any point is an interior of some convex polytope. Okay. If you don't understand this definition, it's time to ask a question about this definition.
Sorry, why convex polytope? Could it be some curved version of a convex polytope?
No. Well, the dependence on the, we are talking about fiber over one point. So the polynomial dependence is on the point in the base. But in each fiber, the defining equalities and inequalities are affine.
But these functions phi are not linear; they are polynomials.
It
Yes,
doesn't matter.
They depend phenomenally on the base.
Okay, I see.
But over a concrete point in the base, what we want is just some affine inequalities and equations. Okay, yeah. For example, we can, yeah, let me give one more example. Say, suppose R1 is a set of P1, P5 of 5 points, such that P1, P5 in this very order is a convex pentagon. And R2, we just add one more point, such that, well, P1, P5 is a convex pentagon, and P6 sits in a central cell of P1, P5. Well, meaning that if you have P1, P2, P3, P4, P5, and you want P6 to sit there.
Then maybe you can shift it a little bit higher.
Yeah.
Thank you.
Yeah, and you want P6 to sit in this colored region. So then you have a projection from here to here, just forgetting the 6th point. And it is indeed a stable projection because, well, where does your point should live? Well, it should live in some, well, you just write that it should lie on the same side of the line P1, P3 as P5, and so on. And you get some, well, polynomial dependencies that determine this region. So this projection is indeed stable. Okay. Are there any questions? Okay, let's move on then. Yeah. And yeah, these were stable projections. And now we define rational equivalencies. So if we have two primary basic semi-algebraic sets, then they are called rationally equivalent if there are rational functions, I'll say phi1, pm from Q to, well, they are a rational function. So big phi is just a rational function from Rn to Rm. And also, I'll say, we have rational functions that define a rational function from, well, in backward direction. And we demand that phi on V should be a homeomorphism, and phi on W should be also a homeomorphism, and that, well, these rational functions, they just give you an identity. So rational equivalent is just a rational function, well, birational map from Rn to Rn, such that homeomorphically maps one semi-algebraic set to another.
Оля говорит, что надо исправить фи на пси в самом низу.
Yes, indeed. Thank you. Yeah, I'm not sure I can read the chat. I can make it. Can try to make it visible for me. Okay. Not really. Okay. Sorry. So I won't read the chat. So if you want to say something, say it in voice, please. Okay. So, and now we are ready to define stable equivalences. So V and W are stably equivalent if they lie in the same equivalence class generated by stable projections and rational equivalences. So yeah, it's not very well. The definition is constructible. Like, while they are stable equivalences, there is a chain of rational equivalences and stable projections such that it goes from V to W. Yeah, but there is, I think, no more clear description of what is stable equivalence. The good thing about stable equivalence is that if V and W are stably equivalent primary basis and algebraic sets, then, well, first, they are homotopy equivalent. And second, I don't know, let's say, there are some algebraic points in one set if and only if there are points in another set for any subfield of algebraic numbers. So yeah, so the questions about whether you can, I don't know, represent you're given a face lattice and you ask some question like if you can draw these polytopes with this face lattice such that all vertices in have all vertices have rational coordinates. So for questions like these, you can pass the stable equivalent semi-algebraic set, and yeah, the answer will be the same. I don't know. We can try to.
Sorry, homotopy equivalent must be stably equivalent, yes?
No, suppose they are stably equivalent. Then they are homotopy equivalent.
Sorry. Okay.
Yeah. Also, well, stable equivalence is even better. Like it actually preserves the singularity structure. But well, to formulate it, it's a bit tricky. So I will just say remark free singularity structure is preserved also. So okay, yeah, for homotopy equivalence, it's really easy. Like, well, rational equivalence is just a homeomorphism, so there is nothing to prove. And for stable projections, well, as we said, well, we have a fiber over a point. It's just a convex, just the interior of a convex polygon, of a convex polytope. So, well, let's construct a section to a stable projection. Say we can take, I don't know, a barycenter of this polytope over each point. Then it depends smoothly, well, even polynomially, on the base. And of course, the composition is, well, and it gives you a deformation retraction of the set V to the set W, because I don't know, you just, well, over each point you have something like this, and you have your distinguished section, and you just linearly homotope the identity map to this section. And since we have complete control over what's going on, like everything is polynomial, then of course it's continuous, and yeah, we get a deformation retraction. And for the second part, well, if there is a point in, yeah, okay, for rational equivalences, it's again trivial because, well, the computation of a rational function, well, when you compute a rational function, you stay in your field. And for stable projections, well, suppose we have a point in this thing, a point, some v prime, well, then v is a point in this thing. And, well, I think other direction should be a bit trickier. And we want to find a v prime. Well, let's find it actually in, let's v prime be even rational. Yeah, you can do this because, well, what do we want from v prime? You want it to lie on some affine subspace defined by an equation with rational coefficients. And in this affine subspace, you have some strict inequalities. So v prime should lie in some open set in a rational subspace. So yeah, of course, you can choose v prime with rational coordinates. Okay.
Daniel, there is a question from Ola. Could you please look at the chat?
Okay. Okay, I don't really get the question. Wow. yes, they are. Well, yeah, if you have, say, on a plane, you have two lines. This line is x equal to y equal to x quantity of 2, and this one is y equal to 1. Then, well, they are not rationally equivalent. But but the thing is that we don't actually get any sets with irrational. Wait a second. Yeah, okay. So sorry, all our semi-algebraic sets, they are already defined over integers. So yeah, all the equivalences we consider are also defined over, well, should be also defined over integers or rational numbers. No, nothing is actually linked to well, yeah, it's a geometry that linked somehow to rational numbers, because what we want to do, we want to somehow give an algorithm to compute something, well, in the end, well, kind of. And yeah, you can't really compute with real numbers. Well, yeah, something like this. Sorry, I don't think it's a sufficient explanation, but yeah, that's it. Yeah. Okay. Are there any any other questions? Okay.
I haven't heard the answer. Maybe you ask Oля to ask in Russian, and you'll answer in Russian what they want, because there was no answer. You make reference to something very vague, algorithm. There was no algorithm here till now.
Yeah, but yeah.
Okay, we can.
Well, do you have a better answer for this question? Probably, because
I don't understand the question.
yes. Well,
The question was about definition. Please refer to definition and understand what is wrong in the answer or in the question or something like that. That is the point.
well, okay.
And for
Yeah.
this, maybe Oля would specify her question.
Okay.
There could be no plane x equal to square root of 2 in your statement, because your polytopes were
Yes. Yes. Yes.
from the very beginning they were
That's what I
interiors
said
of
already. Yeah.
the rational polytopes. That's the point.
Yeah. Yeah. Everything is defined over integers. Yeah. So, Olga, do you have? Okay. Can you specify your question or?
Pardon me for intruding. Yes.
Okay. Yeah. Everything we define is already over integers. So yeah, kind of.
Yeah, I think Oleg just has some problems with sound, so she only uses chat. But it seems that her questions are more or less answered. So she had two questions, one about these two planes, which I think is answered, and another is why in general we want rational coefficients. And then you said about algorithms, which I think also makes sense, right?
Yeah. Okay. So yeah, we'll come to it. Um. Pum, pum. Pum, pum. Yeah, okay. Yeah, let me also formulate an accessories that, well, we in the beginning we chose some bases, and in fact for different choice of bases, the corresponding realization spaces are stably equivalent. And the same for polytopes. Well, in fact, they are not only stably equivalent, but they are already rationally equivalent. Okay, you can think about it. And now we are ready to formulate the theorem. So, theorem by Nikolai Mamaev, 1968. Well, first, for every primary basic semi-algebraic set, there exists an oriented matroid chi such that V is stably equivalent to the realization space of this matroid. Okay, yeah, and since for different choices of bases we get stably equivalent things, we'll just say that this is a realization space of matroid and this is a realization space of Q, without specifying what base we choose. Yeah, and second, well, the same for every. There exists a polytope Q such that our set V is stably equivalent to realization space of this polytope. And this is an original theorem from 1986. And well, all the proofs that are known, I think they first use some normal form for a primary basic semi-algebraic set. And then when you deconstruct your set, you're defining polynomials into elementary pieces, then you encode your elementary operations by geometric constructions. Yeah, and what this is what we will do, but I think we will prove even more general theorem. So first we need partitions, and then we will formulate universal partition theorem. Okay, if you still have some troubles with stable equivalences, I will remind the definition now in slightly more general context. So, suppose we have some primary basic semi-algebraic set and a number of polynomials with integer coefficients. And for any collection of signs of these polynomials, we define a subset of V, well, such that the sign of polynomial is prescribed. And, well, a collection of these, we'll get some certification of our set V. And this certification is called a partition of V. And now, yeah, we need a definition of stable equivalence for partitions. And actually, well, for any, let it be a pairwise disjoint family of primary basis and algebraic sets in Rn. What is a stable projection? Wow, okay. Stable projection from family W to family V well is again you just you choose all these phi's, you choose all these psi's, and you say that they give this collection again that gives stable projections for each Wi to Vi. Okay, so now you just choose polynomial maps such that they parameterize all of your sets simultaneously. Yeah, and then
sorry,
again,
why do you need several sets now? Why do you need several sets?
Well, because I want to prove a result not about one primary basic and algebraic set, but about the partition of them.
Okay, is the phi and psi, must they be the same for each of these sets?
Yes, they must be the same.
Okay.
And the same, yeah, and also, rational equivalence is again rational equivalence. You get this phi big and psi big, and they should induce a homeomorphism on each member of this family of primary basic and algebraic sets. And again, these families are stable equivalent if they are equivalent under their equivalence relation generated by rational equivalence and stable projections.
Is it the same as if you consider just the unions of these sets and then look at stable equivalences which preserve a given partition?
Well, the union of these sets is not a primary basis algebraic set.
Okay.
Well, because because you can't always remove the or in your formula. Yeah. Okay. And now a universal partition theorem, which was also claimed by Mamaev later in 1991. And it stated for any partition V of Rn, there exists a collection of arranged matroids such that V is stably equivalent to the partition generated by these matroids. Okay, so, and of course, from this universal partition theorem, the original universality theorem follows. Let me put it here. Well, because for any, well, because your semi-algebraic set, it is defined by some equations and inequalities, and so you can just consider these equations and inequalities, and then consider a corresponding partition, and your initial semi-algebraic set will be a part of this partition, so it will be stably equivalent to a part of this partition, which is exactly some realization space of matroid. So it is a more general theorem, and it is a theorem we will prove. We'll give a proof, not the initial proof by Mamaev, if there was any. And well, I mean,
excuse me, Daniil, could you please give some example of a partition, and so it doesn't have to coincide with the realization space of a matroid, right? So maybe you can give such an example where it does not coincide, but is stably equivalent to it, right?
okay. Well, I don't think I can give an example of a partition which does not coincide but stably equivalent. No, I can't give such an example. But yeah, but I can give, I don't know, an example of some partition showing that actually partition, well, can be, well, even on the plane, I don't know, the, well, I think it's obvious, but still. On the plane, the parts of the partition can be, say, non-connected. Okay, let it be a hyperbola, and let it be something. Then I think this thing and this thing, this is one part. Because the signs, well, this and this are the same of each of three polynomials.
So these two regions are V1 and V2?
No, these two regions, this is the same part. So in a partition, this partition is not actually like you just draw all the zero sets of polynomials and look what you get. No, you can give more complicated pieces like that are composed from these ones.
So the two shaded regions together are V1, and V2 could be below the horizontal line, for example, or not?
well, these two things, well, these together form V, I guess. Well, if it's the first one, this is the second one, this is the third one, it should be something like 1, 1, I don't know, 1 probably, depending on the equation. This is 1 strata. And if you want, I don't know, strata, say V minus 1, minus 1, 1, then this is this one. This one. And it is connected. So these stratas given by partitions, they can be kind of, even on the plane, they are not that obvious.
Okay, thank you.
Yeah, okay, so now we pass to the proof. Probably we should, no, it's too early. Okay, proof of universality partition theorem.
Sorry, one more question. In Mamaev's first theorem, what about the dimension? So you defined oriented matroids in the two-dimensional case, but in the theorem they are four-dimensional or what?
No, the matroids, well, the matroids are, as we define them, they are for two-dimensional.
Mm-hmm.
But for polytopes, well, immediately, well, yeah, in Mamaev's proof, he first proved the first part and then deduced the second part from this thing. And I think what he can get is that there's the polytope Q of dimension D with some, well, with D plus 4 vertices. This is dimension. This is number of vertices. It is true that there is a four-dimensional polytope, that you can find a four-dimensional polytope such that the realization space will be stably equivalent to your Algebraic set. But, well, it's not that, well, it's harder, it's more technical. Yeah, and I think it can be deduced from the case of matroids. So what we do is we model the computation of polynomials in matroids, and then by Lorentz extensions, we get the case of polytopes. But you can model your computations already on the level of polytopes. And it is done in the book by Richter Gebert. It's called Realization Spaces of Polytopes. And it gives you a proof of universality theorem for four-dimensional polytopes. But, well, we will not prove this theorem today. We'll prove a theorem for matroids, and then deduce some version of universality theorem for polytopes from these. Okay?
Okay, thank you.
Yeah, how do we do this? Let me take a view. How do we do this? Yeah, first, let's talk about quadrilateral sets. Quadrilateral.
So do you now start the proof of theorem 2 or the reduction of theorem 1 to theorem 2?
Okay, well, as I said, well, theorem 2 is this one, yeah? Theorem 1 is this one. Yeah, well, it's, as I said, it's obvious that theorem 1 follows from theorem 2.
Okay, okay. Mm-hmm.
Yeah, you just, for any semi-algebraic set, you just take a partition in which this set is a part. And as you get stable equivalence of partition, then you get stable equivalence of the corresponding parts of the partition.
Okay, so what remains to prove is this universal partition theorem, yes?
Yes, and also then to deduce for the case of polytopes, well, to deduce from the case of arranged matroids, the case of polytopes. Yeah, okay. First, we prove the universal partition theorem.
So what about making a short break?
Yeah, we can make a short break, yeah.
Is now a good time?
Well, yeah, because, well, the proof is kind of involved, and I think we don't want to make a break inside the proof. Yeah, so, okay, we can make
All
a break.
right, so maybe just 5 minutes?
Well, probably, yeah, okay, 5 minutes.
Or you want more?
No, I don't really care. Okay, yeah, so see you in 5 minutes.
Okay.
Okay, I'm back. How can we know that everyone else is back? Please raise your voice if you are back.
I never left.
Okay.
I'm
Yeah.
here.
Sergey.
I didn't really understand the question.
Yeah. Well, you are here, but the other Sergey,
Ah,
are you here?
I'm here.
Okay. So I think we can continue. Yeah. So, yeah, quadrilateral relations. Well, for 6 real numbers, we define its quadrilateral ratio is as this thing. Well, yeah, the plan is as follows. First, by these quadrilateral ratios, well, you can notice that this is just a product of two двойное отношение, how's it called? Of two okay, there is a projective invariant, the only projective invariant of 4 points on projective line, which is called double ratio, I guess. And our quadrilateral ratio is just the product of two of such guys. And thus, it's also a projective invariant. So it's invariant on the projective transformations of a line. And, well, you can define this thing not only for real numbers, but if you insert infinities here and there, say this thing is just this thing, because infinity minus whatever is equal to infinity minus whatever. And if you insert two,
it's called cross ratio.
Cross ratio. Thank you. Well, these are, yeah. So our quadrilateral ratio is just the product of two cross ratios, and thus it is a projective invariant. And this thing is just this guy. We will use these relations to model addition and multiplication. Namely, one can easily compute that if you take this thing, or if you take this thing, or if you take this thing, or if you take, sorry, it's getting a bit tedious, this thing, then they are all equal to 1. So for, if you fix 0, 1, and infinity on your line, then you fix a projective scale, and thus by checking these quadrilateral relations, you can check whether, well, 2 points are, well, you can check if 2 points give you 0 in sum, or if you can, or you can check that 2 points. Well, that the sum of 2 points is the third point, or you can check that 2 points are inverse to each other, or you can also check that the product of 2 points is a third point. And well, now having some polynomial, we want to compute it using elementary additions and multiplications. And of course, you can do this. But yeah, okay, we need some technical lemma. If you have any partition, it's a partition of Rn, then you can find another partition of numbers greater than 1, such that these partitions are stably equivalent. Yeah, well, how to prove it? First, we define an intermediate partition. It's a partition of the following set. It's a basic primary semi-algebraic set. And if our initial partition was defined by some polynomials f1, etc., fm, then this partition is defined by the same polynomials by 1 fm, but now we consider them as polynomials in variables x1, xn, y1, yn. And then from this partition, we get a partition that we want, and namely it's partition defined by f1 of u minus v and so on, fm of u minus v. These are polynomials in u and v. And well, we have our partition nu, and partition w prime maps to it just by sending xy to x. And well, each fiber is defined by these equations. So it's a stable projection. And also, w prime is mapped to w by sending xy to what? To this thing. Well, it's just a sum, well, just some affine transformation, and thus it is of course a rational equivalence. And you see that since y's were greater than the absolute value of x, this thing and this thing, they are greater than 1. And well, they are exactly defined by these polynomials. Well, because because x is just this thing minus this thing. So these are exactly polynomials that define this w. Let me draw an example, probably. Yeah. If you have some partition defined by a polynomial, the x squared minus 1. This is 1, this is minus 1. So we have how many parts? We have, well, this part, which we label by B. We have this part, which we label by A. And we have these 2 points, which are C. What happened next? What is W prime in this case? You just lift it to R2. You draw a graph of the absolute value, and and what you get is, well, this thing is C1. This is also C1. This thing is A1. This is B1, and this is B1. So we get this partition. And then we just rotate it and move and obtain the following partition. This is A2. This is C2, this ray. This ray is also C2. This is B2, this is B2. So, yeah, well, the exact formulas might be irritating, but yeah, nothing very intelligent happens. So, yeah, we just proved that every partition is self-equivalent to a partition of numbers greater than 1. Okay, and now why do we want it? We want it to, well, because we want to compute something, and we really like to compute with positive integers, not just some integers. So, in order to use only additions without any subtractions. So we have some polynomial, and well, we decompose it into a difference of 2 polynomials with positive integer coefficients, and a computation of such a polynomial well, we decompose it into elementary additions and multiplications. What it means, let me show it on the example. Suppose you have like some polynomial. And what is it? Well, it's x times x plus 1 plus 1 plus 1 times what? Times y times y. So we just decomposed, well, a polynomial into a composition of simple additions and multiplications. And for any pair of brackets, we introduce a new variable, which we call this one. So vx squared is just x cross x. Vy squared is y cross y. V2 is 1 plus 1. V3 is V2 plus 1. V3 y squared is V3 times Vy squared, and Vx squared plus 3y squared is Vxy squared plus V3y squared. So for any any elementary, well, first we introduce some, well, we have some variables x and y, and then for any elementary addition and multiplication, we introduced a new variable, and we just wrote some polynomial equations of a very simple form, such that the last variable we introduced is, well, actually the value of the polynomial. This thing we will call a computation of a polynomial, and let me formalize it into a lemma. If you have a polynomial with natural coefficients, then we can introduce some new variables, and we can say that something, well, there are some additions, there are some multiplications, let's call it m. Well, these are just, well, x, y, z are some elements of the variables we introduced, and 0 and 1. Well, such that if you take any input, then there exists a unique solution of this. Well, we have some system of polynomial equations. So there should exist a unique solution of this system. And moreover, x1, xk, they are all greater than 1. And the last variable is equal to the value of the polynomial computed at the input. Well, yeah, it's what we did. Well, why are they all greater than 1? Because our initial numbers were greater than 1. And what we do is we add something or multiply something. And if you do it with numbers greater than 1, then you get again a number greater than 1. And yeah, so yeah, we've just proved the lemma. And okay, are there any questions about this lemma?
It seems that you could shortcut it as an arithmetic straight-like program. This is a notion from computer science. Okay, pardon me.
Yeah. But probably not everyone is familiar with computer science. So yeah, it's really easy. Yeah, there is nothing. Yeah, you just And now, what you want to, okay, you have some system. Well, you have a number of polynomials, and now we know how to do a computation of these polynomials, and we want to encode this computation into quadrilateral relations. Now, how do we do this? So how do we do computations with quadrilateral relation?
Pardon me, but it seems that you could transform what you speak just in the language of computer science. It may be more appropriate, but because it seems that you simply change the signature, change the basis of the basic operations in the scheme. It's just a transformation to scheme. In some audiences, it would be better to use this language, pardon me, but no, maybe not in this audience, yes?
Yeah, probably.
You change the basis, the basic operations, the signature of the arithmetic scheme. It's the, and by the way, there are a lot of people in Peter, in Leningrad, I don't know, who are very much involved in schemes, their complexity and all that.
Yeah, but well, I want to introduce some more notation. I want to just,
Pardon me.
Keep it as elementary as it can be, I don't know, it's helpful. Probably probably some notation would clarify things, but yeah, it is the way it is. Okay, so what we do next? Yeah, we just compute via quadrilateral relations. So for this, we need a notion of a cluster. And a cluster is just, well, X is just an ordered collection of variables such that 0 and 1 are among them. And, well, Q is some collection of quadrilateral relations. A quadrilateral relation is, well, you just say that your quadrilateral ratio has, well, is either greater than 1 or smaller than 1 or equal to 1. So A, B, C, the F are our variables, and sigma is some sign. Okay, and also let me denote by, well, the smallest element will be x0, and the largest element will be, well, xl. Yeah, this is the notation for B with arrows, and yeah, what do we say? For a given collection of real numbers, we say that they satisfy this cluster if first they are linearly ordered, and second, well, and they satisfy Q. And the next lemma we need is just that we can indeed make the computations via quadrilateral relations. So suppose we have some partition. E of numbers greater than 0 to the power n, which is induced by polynomials f1, etc., fm with integral coefficients. Then there exists such a partition let me write. There is such a partition of some r to the big power which is, well, okay, any partition of this set is equal to some partition induced by quadrilateral relations, meaning that this thing is equal to 1, there is some collection, and also there is some other collection of quadrilateral ratios such that, well, for this collection, this collection gives us partition for 1 to m. So this lemma basically says that every partition you can there exists such a thing such that, of course, this is stably equivalent to this. So every partition is stably equivalent to a partition induced by quadrilateral relations.
Daniel, there is a question from Ola.
Yes. In the definition of Q, the the six tuple is ordered, and yeah. Well, and you can, well, okay, you have some numbers, and your Q looks like a collection of these things. So for each of these A, B, C, D, E, F, you know its value. So you just substitute it. You compute your quadrilateral ratio, and you check if this is true. Yeah. So everything is ordered because our quadrilateral ratios do depend on the order. They change sign if you change the order. I can't find the definition, but yeah, well, they do change sign. So
another question.
Okay. Okay, you have some numbers, and you have a collection of, I don't know, this Q. Say it is something like sine of x10, x9, x1, x3, x4, x5 minus 1 is equal to, I don't know, to 1. You are given all these numbers. You substitute here. You substitute here. You compute Q. You subtract 1. You compute the sign, and then you check if the sign is as it is prescribed. And Q is just a collection of these relations. And for every such relation, you check it. And it means that, well, if all these relations are satisfied, it means that these tuples satisfy Q. Okay? Okay. Let's move on. Now I want to prove this lemma. How do we do this? Well, straightforwardly, actually. Like, how do we do this? Prove this lemma. Well, first we decompose every polynomial into the difference of two polynomials with natural coefficients. Then we compute all these polynomials. Well, with computation of these polynomials, we get some variables. We have initial value variables, and then we get a bunch of variables. These are all variables needed to compute fi plus, fi minus for all I from 1 to m. Okay, we have a bunch of variables. And let's say that the total number of additions in our computation is NA, number of additions. And well, NM is number of multiplications. And S is M, because I have M polynomials, number of sign conditions. And NV is number of variables. So, and now we introduce several clusters. First, we say that there is -1. So we introduce a cluster with 3 variables and 1 relation, namely that (1 plus -1) is equal to 0. This is our first cluster. Then, for any variable, we introduce we introduce its own cluster. What is this cluster? It says that, well, we have this variable, and also we have minus this variable, and 1 over this variable. And we will, well, and these v's are new variables. And also we have zeros and ones new for each new cluster. Then later we will somehow glue it, but not now. And yeah, so, and what you say is that, okay, we know that we can write these quadrilateral relations that encode that, I don't know, that this thing plus this thing should be equal to 0. Okay, let me write it. So the first relation says that xi plus minus xi is equal to 0. And the second one says that xi times times 1 over xi equals 1. Then, for any addition, we also introduce a cluster. So, well, suppose we have if elementary addition, and it is of the form that xi plus xb is equal to some xc. Then, well, we just say that it's the next cluster. And this cluster is, well, it basically says that in the language, it says in the language of quadrilateral relations that xa plus xb is equal to xc. So it just says that for multiplication, we do the same. And then for sign condition, well, what is a sign condition? Sign condition is something about fi. And, well, we don't compute fi. We compute only fi plus and fi minus. So say xa is fi plus, and xb is fi minus. Then we say that, well, it's some next cluster. We need to number them, like, because we want to glue them after it. So we need a number. Yeah, and you say that, well, you have these no. But, well, yeah, you need, what do you need? You need the sum, the difference between this and this to be positive or negative or equal to 0, right? So that's what you do. You introduce variables, these variables, this variable, and yeah, and you say that the sign well, it is prescribed by the sign, which is given by partition. So now we introduced, well, some clusters, and, well, what we do is we need to ensure that the variables we introduce, they are actually somehow related to each other. Like we have many variables that are actually one variable. And for this, we introduce linking relations. And basically say that, well, if you have some variable, well, this variable w can be some xi or 1i or v something I. So for any such variable, well, you can have wi, you can have wj, and you want them to be equal. So it means that on the projective scale for wi and on the projective scale for wj, you can compute the values of wi and wj, and they should be the same. It's what we want. Well, and we ensure it by the quadrilateral relation. By this quadrilateral relation. And also, you want a linear order on all your variables. And for this, you identify the last variable of one cluster with the first variable of the next cluster. Okay, let me draw an example, I guess. Now, around this, well, some people might be lost, so I will draw an example, and I think it will make things clearer. Suppose we have a polynomial. I don't know.
Sorry, Daniel, what do you mean by identifying them?
I mean that you say that, well, these things are the same, they are equal. Well, you well, you just enforce it. Like you say that, well, you have 2 points, and you say, well, these are the same points.
Okay, maybe
an example, it will become clearer.
Okay.
Okay, suppose we have this polynomial, very easy one. From this polynomial, well, we get a polynomial in 2 variables, which is this one. Well, this was a polynomial defining some partition, namely the partition of a line well, in 3 parts. But we want not a partition of a line, but a partition of a number greater than 1 to some power. And our, well, some of our lemma gives us this polynomial. So it's a partition, well, it's partition of this is 1, this is 1, this is this partition. Again, in 3 parts. 1, 2, 3. Now we want to compute this polynomial. How do we do this? Well, first we decompose it into, well, f plus of x1, x2 is x1 plus 1, and f minus of x1, x2 is just x2. And what do we do to compute it? Well, we introduce a new variable. Now we introduce a variable x3, which is equal to x1 plus 1. This is x3. And now, what do we do? I lost my. Okay. Okay. Now, what clusters do we introduce? Well, first, we say that there are some numbers -1, 0, and 1. And well, for them, we say that, well, this is the 0th cluster. If I can find it, would be really, yeah, okay. Probably I can do it like this. No, it doesn't really work. Okay, I will just show it from time to time. Okay, this was the 0th cluster. Then we introduce the next cluster. Well, this next cluster, let's just number. Well, we say that we identify the first point in the first cluster with the last point in the 0th cluster. So this cluster, it determines a variable, namely a variable x1. Yeah, this cluster determines a variable x1. So we need 1, 2, 3, 4, 5. 5. This is a cluster B1. Let's call it Y1, Y2, Y3, Y4. And well, in this cluster, these variables have the following meaning. That it's this thing, this thing. Well, exactly as we do by definition. Then we take the next cluster, which again determines a variable. Now it's x2. So we need to add 4 more points and say it's a new cluster determining a variable x2. Then we take the next cluster. Well, it should determine the variable x3. So again, we add 4 more points, and it's a next cluster. Okay, all variables we needed for computation of our f plus and f minus, we already determined them. Now we do one addition. Well, for addition, we need 4 variables. So we need 3 more, and we get a new cluster for addition. It's B4. And finally, we have one condition. And for a condition, we need 3 variables. We need 3 variables. So we add 2 more, and we get the last cluster. What do we do next? Next, we say that, okay, we've determined all the well, some numbers, yeah, and now we also say that they should satisfy some more relations, for instance, like this. So what do you have? It's really okay. This is addition. So for addition, I think we have x3, 4 here, and we have 0, 4 here, and we also have x3 in the definition of x3, and well, so this is x3, 3, and this is 0, 3. So for these 4 points, namely this one, this one, this one, and this one, we should impose a new quadrilateral relation. And so we do this for all variables that are the same, but for some reason, well, for some reason have different upper indices. And points of adjacent clusters we have already identified. Okay, now what have we actually done? What have we done? Yeah, sorry, just a second. Okay, yeah, suppose we have some input, which is x1, xn. From this input, using the relations, well, using the clusters from 0 to m, meaning 0 variables, additions, and multiplications, and also using linking, we actually determine all the variables, well, we have -1, less than 1, y, and so on, yn. Yeah, so we had some numbers, and from these we, using the quadrilateral relations, we produced some y's that satisfy these quadrilateral relations. These are also numbers satisfying these quadrilateral relations. And well, in each of the cluster, one can just check that the ordering is correct, and we forced our clusters to decompose in such a way that, well, that this thing lies in two clusters. So in each cluster, we have a total order, and then we lose total orders. So we have a total order on all variables. And from the relation S, we get assign conditions. And so basically, we are done. So these y's, we get them from x's by some just rational functions, right? Just we say that, well, some relation should be satisfied, so y1, say, should be equal to something, because we have this thing already fixed, and and we know that the difference between this thing and this thing, say, is the same as the difference between this thing and this thing, and so on. So we determine all the values of y's. And how do we go back? Well, we just look at our numbers and we say that, okay, there are some, well, there is some y corresponding to, say, xy, xii, and there is some y corresponding to 0i. And if we compute just the difference of these two numbers, then, well, we will get the same thing, well, for any upper index, and this is exactly the value of xi. So we go from xi's to yi's by rational maps, and we go back also by rational maps. Well, stupid ones. So they are rational equivalent then. Yeah, please ask me a question. Doesn't make any sense to you at all. Like, yeah, probably I will explain it, but yeah, ask a question.
So Sergei Tarasov had a comment in the chat.
Well, yes, probably, but well, the realization of arithmetics without subtractions or without divisions, well, it's not the I don't think it's the main difficulty like here. Like we nonetheless need to check those quadrilateral relations. And so yeah, but probably it would be more clear. Okay. Any questions? Okay. Okay, fine. Then let's say we prove this lemma. And now what we need to do is we need to somehow go back to our ranged matroids. So we need to encode the same additions and multiplications by some point configurations. And well, okay. If you are lost, then you can now get back because it will be easy now. Suppose you have a 0, you have x, you have y, and you want to compute x plus y. How do you do this? Well, you can do it like this. You take some point on the parallel line. You draw these two segments, and then you just draw from this point a segment parallel to this one, and a segment parallel to the second segment. And then you get x plus y. Okay? And well, you can now map this picture, well, apply a protected transformation to this picture in such a way that the infinity goes to some finite point. And then you'll get the following picture. Let me draw it. Should I probably draw some other picture? Wait a second. Okay, and if you want it minus x, okay, suppose you, yeah, minus x, you can do the same. Yeah, okay. So now we apply to this picture a transformation that maps infinity to a finite point. So we have the first line, this is this one, the first. And the second line, which was parallel to it, now intersects it. And let me denote only 0, minus x, and y. What did we do? We chose a point on this line. Okay, let's choose a point. And then what did we do? We Okay, let me draw another picture. Sorry. Okay, we have only 0, minus x, and y. What do we do? Well, first, choose a point and call it A. No, it wasn't work like this. Sorry again. Let me think. Okay, yeah. One last try. Choose a point and draw like this. Then draw a parallel line. And then draw like here, and then like here. Yeah, that's what we wanted. Okay. Yeah, sorry for the delay. Yeah, suppose you want to, from 0, y, and minus x, you want to get x plus y. How do you do this? How you can do this? Well, first you choose a point B and draw segments minus xb and by. Then you draw a parallel line. Then you get an intersection point of this segment and this line, and you draw a line through it, and you get a new point on this line, and then you get another intersection, and you get your x plus y. Yeah. So yeah, and well, this thing is equal to this thing, and this thing is equal to this thing. So great. And now we apply projective transformation, and what we get is, well, pretty much the same picture, but just with infinity. So this is A, and this is B. This is x plus y. So we've just modeled how to get x plus y from minus x and y if you fix it on your line 0 and infinity. This was the picture when infinity is at infinity, and this is the picture when infinity is at some finite point. Are there any questions about this construction?
In the picture with parallel lines, you don't need the third line to be strictly, to cut it strictly in half, to have the same distance from the first and the second line.
Yes, you don't.
Mm-hmm. Because you mentioned that the segments from 0 to minus x and from A to B are equal, if I understood correctly, but actually they don't need to be equal, right? So there are similar triangles, I think.
Yeah, thank you. Well, yeah. And yeah, so we have the same picture. On this picture, it's clear from school geometry. And if we apply projective transformation, we get this picture. And you can basically do it for any of the quadrilateral relations you needed. What were relations we needed? Well, we needed to have some minus x, y, 0, infinity and x plus y. And we needed a relation for opposite numbers. And for opposite numbers, well, the relation is like this. It's infinity, it's 0, it's minus x. You do like this. You draw a line again. You do like this. You do like this. And here you are, you go, you get your x. So, yeah, but let's focus on these two. And now we want to say that suppose we had some quadrilateral relation. We want to draw a picture such that it ensures this quadrilateral relation. And it's exactly what we do. So, the algorithm. What do we do? Let's okay, suppose we had some x1, xn, which was a point of a partition. From this, we construct y, we construct y's. Then we put these y's on a projective scale. So we just say that, well, we fix infinity, 0, and 1, we get a projective scale on a line, and then we have some numbers, y, etc., yn, and well, we have them somewhere, y2, y3, etc. And then, well, we draw another line. And now what do we do? Well, we have some relation concerning these points. Say that, I don't know, that I don't know, some relation. And for each such relation, what do we do? Well, we have this picture. Well, so if, yeah, suppose we want to say that y1 plus y2 is equal to y3. Yeah. So first we need to construct minus y1. And for this, we just, well, we draw this picture. We choose A and B. We choose them close together. You construct your, well, okay, let me do it. We do like this. You do like this, do like this, do like this, and what you get here is minus y1. And then you want to say that, well, minus y1 plus y2 is equal to y3. How do you do this? Well, again, you choose, well, this was A1, B1, C1, and D1. Now, for the next quadrilateral relations you want to encode in your point configuration, you choose your A2 very far away from this configuration. Very far away means that you don't want any line that was drawn before well, you want any line you have drawn before to intersect your ray before your next point. Okay, you chose this point A1. You choose your point B2. You draw a picture for ensuring that Y2 plus Y1 is equal to Y3, and so on and so on. So what do we actually obtain? Well, from any set collection of y's, we obtain a point configuration. And the fact that these y's satisfy some quadrilateral relations is a fact about these C's and D's. And the picture is exactly like this picture. Oh, that's, by the way, why they're called quadrilateral relations, because, well, this is a quadrilateral. Yeah, okay. And then we ensure every quadrilateral relation by these things. And then what we do next, we want we have some sign conditions, right? And for sign conditions, we also can draw a thing like this, but with point C being not lying on these, well, with the intersection of these two segments not lying on this ray, but rather being below or above this ray. And so, and that's how you encode the quadrilateral relations that are not equalities but inequalities. And that's basically it. So now we need to check what happens. Well, what is our freedom in choosing these A's and B's? Well, our freedom is restricted by some polynomial equations. Like, you want first that they are far away, which means that, well, these lines, they should intersect it before this point. And also you need to, well, and yeah, and also you have some equality saying that, well, A and B, they are related. So your choice of A and B is well, it is a stable projection. No, sorry, yeah. Sorry, and yeah, that's basically how we do it. Please ask a question.
So your point configuration in this example, as I understand it, is A1, B1, C1, D1, A2, B2, and so on, right?
Yes.
So it certainly encodes the information about the polynomials that you originally had.
Yes.
But, is this all that we wanted, just to encode this information?
No, we wanted so that, well, that when we have the configuration with the same well, like with the same oriented matroid, then it should also give us these y's. This is yeah, this is also true, because, well, if you have such configuration, then since you are interested in things that are far away, and this in this thing, well, the picture is exactly the picture that encodes you that, I don't know, that this is minus this, then this is indeed a minus this. Like, yeah, so we encode our quadrilateral relation in this point configuration, and we can recover this relation by a point configuration. Yeah.
Okay, so have we proved the theorem?
Yes, well, at least sketch the proof. Yeah, but yeah.
So can you please show the statement of the theorem?
Oh, well. Here it is. Okay, yeah, let me briefly recall what we did. First, for any partition, we make it into partition of numbers greater than 1. Then we encoded it. We proved that every partition is actually can be obtained from quadrilateral relations. And then we, for such a partition obtained from quadrilateral relations, we encoded it into a point configuration. So we've got that every partition is stably equivalent to a partition coming from a point configuration.
Okay, I think the idea of proof is more or less clear to me.
Okay, so probably, yeah, I don't think we have much time left, but I want to just sketch the passage from related matroids to polytopes.
Aha, Daniel, there is a question from Ola.
Let us look at what we did. But the answer is yes. Well, because if you when you realize your relation, your quadrilateral relation on a picture, you have your infinity, not infinity, but well, as a finite point. So for this, you like it is a projective invariant, but when you want to draw it, you need to really compute something with these finite numbers, and you need 6 of them. No, not only 4. Does that answer your question? No, okay. Okay. Okay, what quadrilateral relations we really need? We need this one. Yeah. And one may say that these are only like cross ratios. Well, yes, but look, we have this picture, and how to put it better? In this picture, quadrilateral relation of this form is actually a quadrilateral relation to which we on which we performed a projective transformation, and it no longer is just a cross ratio. Like you really have these, well, you have these points, 1, 2, 3, 4, 5, and these are real points. These are real points on the line. There are 5 of them, and well, it's not a cross ratio then. Does it make any sense? Okay, so probably I can answer a question in this fashion. Well, yes, every quadrilateral relation, as I wrote, is just a product of 2 cross ratios. Any. But, well, why do we want a quadrilateral relation but and not cross ratios? Well, exactly because we know how to draw these quadrilateral relations in the picture. For a cross ratio, well, we don't. I don't know how to encode a cross ratio into a picture. Okay. 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 Now, yeah, and now I don't know. I think I will take 10 more minutes of your time. I will say just a couple of words about how to go from oriented matroids to polytopes. Okay. For this, we need Lorentz extensions. All the Lorentz extensions. Suppose you have some convex polygon, convex polytope, and you embed it into a hyperplane in some, and you take a point not in this polytope, but in this hyperplane. And you take a line like that it intersects hyperplane in exactly one point. Then the Lorentz polytope of this is the convex hull of 2 points lying on L. Well, where Q bar and Q underbar lie on L. Well, in this order, you have Q this thing, and you have Q this thing. So what actually happens? Suppose you have, I don't know, some polygon in the plane. Well, you choose a point, you draw a line, you take, this is the point Q. You take 2 points and you consider a convex hull of this. Why is it good? Well, first, you can easily recover from this polytope the position of Q, because you just take the intersection of, well, of the affine spine of these 2 points and the affine spine of all other points. Also, the faces of this new polytope, they encode the orientations of these, the orientations of the points here. So basically what you do is you just apply Lorentz extension. Well, okay, suppose you have a point configuration, which is Q1, struct UN. And let's say that Qn-2, Qn-1, Qn, they form a triangle, a minimal triangle, which means that they're not intersected by any other lines spanned by, well, that you draw from, spanned by this point. Well, there is always such triangle. And let's call it triangle P. Then you apply Lorentz extension to this triangle. Well, in every other point, but the points that form this triangle. Well, this thing means that you just consecutively apply it. So your dimension in the number of points they draw, but in fact, what you get, it doesn't got the orientations of your point configuration.
Can you explain in more detail why the Lorentz polytope encodes these orientations?
Yeah, let me try. Okay, let me do it on an example. Suppose we have a triangle, just one triangle. Then what you do? And you have some other point. And you take these things, and what you get, I think in this case, in this picture, it's doesn't really look right.
If the points are generic, then all faces should be triangles.
Yeah. Well, they are now, no?
I see a quadrilateral.
Oh, yes. Sorry. Mm,
But in general, you could have a quadrilateral in your construction. I mean, it doesn't have to be generic, or it has to be.
no, it doesn't have to be generic. Yeah. Well, how do we know that these guys, they lie in this order, not in this order? What is the difference? Between wait. The
I have a proposal. Let's take for granted that what you want to prove is proven. Go ahead. You have said that all the configurations of I don't know what is somehow coded in Lorentz polytope. Okay, go
well,
ahead.
then that's basically all. No, like well, we want to reduce a universal theorem for polytopes from
No,
your theorem.
not for polytopes. From partitions to polytopes
Yes, we know that.
in another direction.
Yes. So yes, and well, then the realization space of these point configurations
Mhm.
is stably equivalent to the realization space of Lorentz extension. Because what is the choice you can make during this Lorentz extension? Well, you just choose where these Q's lie. Each time you add new dimension, so well, your choice is just choosing two points, and it is a stable projection. And from Lorentz polytope, you can get your initial configuration, as I said, by just intersecting the line through Q through these Q's and a fine span of all the rest. And this intersection is your vertex Q, and so on, and you get all your point configuration.
I see. And how to get to the dimension 4? Because now we should know what was the initial dimension of the Mnev proof. D was a kind of a constant, very big, but a constant, where uh, he proved that there is such a dimension, then the configuration space of polytopes is universal. And you have said
No.
that some two guys later proved that the four dimensions is enough. What should we elaborate to get to the conclusion that four dimensions is enough? where?
No, to get the 4 dimensions isn't are enough. You should you should not do what we did here. You should do your computations with polytopes already. Like you don't do this with quadrilateral relations, but you make your elementary computations with polytopes, like with connected sums of polytopes, with some pyramids over the polytopes, and so on. So yeah, so to get the estimate 4, you need to do it from the very beginning without arranged matroids. Like I don't think that there is any proof for dimension 4 that first proves it for arranged matroids and then reduces it for polytopes. So you should do the computations in polytopes already. Although from universality theorem for matroids, you can get dimension 6, but I don't know how to do this. But you can. It's written in Richter Gabbard's book. Does that answer your question?
Yes, I see.
What about non-oriented matroids, usual matroids? Is there such a universality theorem for them?
Well, in this case, I think it should be over C, right? And there is a universality theorem. No, wait a second. Let me say that I don't know. Yeah, I don't know. Like, there is some analog of this universality theorem, but I don't know how to state it.
But why?
Because, well, you don't have semi-algebraic sets of complex numbers.
Why do you want to do it over complex numbers?
Well, okay. Because arranged matroids is something that gives you an abstract notion connected with collections of vectors in Rn. And matroids is something that give you an abstract version of collection of points in Cn. But probably it's not what we should actually do. I don't know.
But why cannot you understand non-oriented matroids as still encoding collections of points in Rn, but just retaining less information?
Yeah, probably you can, but I don't know if you get an universality theorem from this.
Okay.
Excuse me, but I don't understand. Every time you speak about algebraic notion of matroid, because matroid is something more than that. I just don't understand from the very beginning. The oriented matroid may be stated combinatorially, and you stick only to the algebraic version. Is it accidentally, or you just don't need any other?
Well, look, the configuration spaces, the realization space is non-empty for an oriented matroid, even only if it is realizable, just by definition. So all our matroids, they are realizable, so we don't need this abstract definition of matroid, because for non-realizable matroids,
Okay. I see, but when you speak about try to answer the question, search question, you speak about matroids. You should somehow choose what you speak only realizable matroids, because it's some it depends on the field and all that, and they are so well graph matroids that trees and all that. It's very rich notion with different implementations.
Well,
Yeah,
I guess in my question, I meant to ask about realizable non-oriented matroids, realizable over R.
Non-oriented is something which the word which should not used.
Okay.
Yes, okay.
okay. Yeah, well, I speak about realizable Metroids because every time I speak about Metroid, I think I speak about the realization space, and well, if it's empty, then there's nothing interesting. So we are interested only in realizable Metroids.
I'm not sure, because you're speaking of the you try to relate two different languages. The fact that in
Okay,
one
yeah,
language
I think
there some notion of realizability maybe not connected to the realizability in different language. So it should be stated at the very beginning that when I stick to the notion, you stick to the notion of a oriented Metroid, I mean that they are realizable, and that will be okay.
okay, yeah. Sorry
It's
if I
not
didn't mention
evident
it.
from the very beginning that you should choose exactly this part of the notion.
I
Pardon me.
think I think Daniel said this in the very beginning.
Maybe,
Maybe he didn't write it down. Yes.
okay. My fault then.
Okay, other any other questions?
Maybe we'll sketch some perspective, I don't know, of all the things, what had happened since 1999, 91, 1986, I think.
Uh,
What are open problem in the field?
uh, well, a perspective. Okay. Well, there was some application. Well, I don't know any details actually, but there was some application of, well, not exact application, but a counterpart of universality theorems in algebraic geometry. I think it's written in Vakil's survey, which I read, but I don't remember what's written there. And yeah, also, well, the phenomenon of universality was later found uh, in other objects, say in the partition in the certifications of Grassmannians, and I don't know. Well, in other objects. Yeah, and also, well, okay. This theorem basically says that the study of well, the questions about polytopes, about arranged matroids, are as hard as questions about polynomial equations and inequalities. But well, some people, they focus on a good strata. Like they, well, of course, a strata can be bad and a partition can be bad, but it turns out sometimes that there is a good strata, I don't know, like a positive Grassmannian, and on this strata you can do some more research. Yeah, I don't know what to say else.
Thank you, and pardon for the question, yes, because maybe
Okay.
it is
Good
not.
question. Good question. Let me try to add one more comment about relations of matroids to topology. I guess one doesn't have to explain how convex polytopes are related to topology, everybody knows a lot of ways how they are related. But for matroids, it could be not so obvious. But there is one very important place in topology where matroids appear. So one could try to understand differential manifolds, smooth manifolds, in a combinatorial way. So Macpherson had a paper about this. He had an approach to do this. And the idea is the following. He starts from a combinatorial manifold, piecewise linear manifold. And then I think in each vertex of this manifold, or maybe on each simplex of this manifold, he puts a matroid, which records some local information, some local information which could help one to smooth this manifold near this point. So if you have a smooth structure on this combinatorial manifold, then you can certainly record these matroids in all vertices. So there is a way to write down some purely combinatorial object, just a simplicial complex satisfying certain condition on links of vertices, and this matroids, it's finite combinatorics, which maybe encode smooth structures on PL manifolds. But this is open question. So it seems there have been some papers about this, but with errors. And probably it looks like some part of the difficulty comes from this universality theorem. There are too many matroids in some sense, and it's difficult to work with them. Okay, thank you.
Sergey, excuse me, but am I right to recall that there were papers by Gilfant and Macpherson in 1982, and then very prominent paper Gilfant, Sergadov, and Macpherson. But since then, there are only reference to that work, and I don't know any. Maybe there are some progress, but I don't know.
What I mean is that something a little bit different. Macpherson alone, without co-authors.
Without co-authors.
I think 1993 or about that time. And then later, there were several papers by Daniil Bliss in very good journals like Annals and Invenciones, where he claimed to prove some things in that direction, but then people found errors. Actually, you can find on the archive a short note by Nikolai Mnev, where he discusses errors in those papers on Bliss.
But is it related to their more advanced technique of Mnev and I think Sharigin, yes, during last years? They try to combinatorialize the characteristic classes and all that.
Yes, I think it is related because this question of combinatorial differential manifolds, it is related to these combinatorial Grassmannians, which are, well, what they study with Sharigin.
Thanks, yes.
Okay.
So are there other questions? All right. So
we should thank the speaker. I should and clap.
Yeah.
Yes, that's
okay. Thank you, Daniel. Very good talk. Thanks a lot.
You're too kind. Okay, thank you, everyone. Yeah.
All right. So goodbye, everybody. See you
No.
maybe on Wednesday or
And
later.
take care. Yes.
Take care. Stay healthy.
Yes.
Goodbye.